Hi everybody, welcome to our webinar. This is a joint webinar between Korvus Technology and Impedans. And I'll just start off by introducing our hosts for today. I'll first introduce our delegate from Impedans, Angus. Angus earned his degree in physics and with astrophysics from Queen's University, Belfast. This was followed by a PhD in plasma physics from Dublin City University, and then went on to work as a process engineer in the semiconductor industry and a few business development roles in various different sectors before becoming a sales manager at Impedans for the past 2 years. And our next host is from Korvus Technology, Matthew Clancy. Matt graduated with a degree in physics from the University of Bristol, after which he worked in the teaching sector for a few years. And for the past 2 years, Matt has worked in the global technical sales team for Korvus Technology and has been involved in servicing, installs, and customer support for all of their modular PVD systems. The first section of this presentation will be from Korvus Technology, with Matt leading that one, and it will focus on their range of PVD systems. The second part will then be from Impedans and their role in plasma physics research. At the end, we will have around 10 minutes for any questions from anyone watching. So feel free to put in any questions you might have in the comment section at the side, and we'll get round to answering them at the end. All the registrants will be sent a recording of the webinar after its conclusion. And if we don't get round to answering your question at the end, or if you don't feel like putting a question in there, you can send us an email and we will reach out and answer all questions at the conclusion of the webinar. So without further ado, I'll pass over to Matt and he will take part Korvus Technology's first part of this webinar. Thanks, guys.
Thank you very much, Tom. And as you said, this is going to be the Korvus Technology part of the webinar, where we're going to be discussing a few things. So we're going to start off by discussing shortly the role of PVD in the semiconductor manufacturing industry, before going on to talk a bit about why plasma diagnostics may be useful in PVD. And then we're going to discuss a few case studies of our users integrating plasma diagnostics into our PVD systems and some of the interesting results that they got from that. And as Tom said, if you do have questions as you go along, then please feel free to put them in the chat and then we can collect them all at the end and answer any which we don't have time to get around to. Just shortly before I begin the presentation, this webinar won't be dealing with explanations of PVD techniques such as sputtering and evaporation. But if you do have interest in learning more about those, then please go over to our website where we have a video section with a few short animations which explain the techniques in quite broad terms. So to start off, we have a slide explaining a bit about why PVD is used in semiconductor manufacturing. So at its core, in semiconductor manufacturing, you start with a blank silicon wafer, and then through a series of steps of deposition and etching, you end up with a wafer made up of lots of die, like you can see here in this image. And there are a few different ways you can deposit on these wafers, but this process flow shows one typical way. So I'll just run through this quickly. So you may start with a type of metal film, such as gold in this case, which you cover with a substance that is called a photoresist, usually by spin coating. After this, you will then place a mask on top of the photoresist and then expose it with UV light. And depending on the type of photoresist you're dealing with, that UV exposure will either make it more resistant or more susceptible to removal in a solvent. So in this case, the UV light makes the photoresist more resistant and the inner sections are dissolved away by the solvent. After this, you have an etching step. So this is typically done with ions, and there are a few ways of doing this, but in reactive ion etching, the plasma is set up in such a way that it preferentially erodes the underlying gold layer and doesn't erode the photoresist as much. And then after this, the photoresist, or the whole assembly, is put into a different type of solvent, which then erodes away the remaining photoresist, leaving a pattern of metal on your wafer. So this is primarily the use of PVD in semiconductor manufacturing for the metallization of integrated circuits, or die as they're otherwise known. But other materials can be used as well. For example, metal nitrides are often used as diffusion barrier coatings in vias, which are electrical connections between two or more metal layers. And when using PVD, thermal evaporation and E-beam evaporation are still used in some R&D contexts where material usage is quite important, so you don't want to waste any material, or expensive ion etching equipment may not be available. However, in industrial contexts, sputtering is almost exclusively used due to its higher purity, because there are no boats or crucibles involved, and also the ability to integrate plasma diagnostics, which we're going to talk a little bit about on the next slide. So in PVD, plasma diagnostics are useful in either sputtering processes or ion pre-cleaning of substrates or ion etching, because all of these processes use plasma. At its core, plasma diagnostics give an understanding about the number and energy of ion to neutral species at different positions in the chamber, as well as other measurements like plasma potential and temperature, etc. And you can see an image here of a Langmuir probe placed above a magnetron source, for example. So this will give information on the plasma parameters when you change certain things like gas flow, magnetron power, magnet strength, all of these things. So why are they useful? Well, at its core, plasma diagnostics bridges the gap between the setup of your chamber, so the chamber conditions, and the final film result. So if you set up your same chamber in a certain way, so you have a certain gas flow, certain magnetron power, in this case, you have some microwave sources here, so they'll be operating at a certain power. Then you set your chamber up in a certain way, and then after you make your film, you'll perform some ex situ characterization of the film. But if your film isn't the way you would want it to be, then what you end up having to do is pull lots of different levers, such as changing the gas flow, slightly making new samples, measuring those. Then you might want to change the magnetron power and make new samples and measure those. So it can take a very long time to do all this, and you're kind of stumbling in the dark to try and achieve the film that you want. However, if you include plasma diagnostics, then you have a wealth of information on the actual plasma physics and chemistry inside your chamber. And this can be useful for quite a few reasons. So firstly, it can be useful for fast tracking material developments, because the plasma diagnostics give you information on the number and energy of ions reaching your substrate. And this is really crucial in finding the film that you want. So if you know that your film is having better characteristics when, for example, there are a lot of indium ions reaching your substrate, then the plasma diagnostics give you the tools to be able to further increase that, to kind of fast track the material you want. And also you can generalize this to other material classes. So you might be looking at indium nitride, but you can transfer this information to other nitrides. On top of that, plasma diagnostics aid transfer from very small PVD chambers to big chambers. So we call this process transfer. And this is because the same chamber parameters in different size chambers, different shape chambers, will give very different results. So you can instead aim to have the same plasma parameters, which will give much more repeatability. And on top of that, they just aid troubleshooting, because they allow you to really see what's going on and whether something has gone awry in your chamber plasma. So we're going to look at a few case studies of people using plasma diagnostics in the Hexcel. These come out of Bern University and EMPA, which are both institutions in Switzerland. And these papers use a web of plasma diagnostic tools, such as optical emission spectroscopy, to measure emission from the plasma and plasma chemistry And you can see an example of this on the bottom of the hex cell chamber here. Time of flight mass spectroscopy, which determines the species and energy of ions arriving at the substrate. Langmuir probes to measure plasma properties of the substrate, such as temperature. A modified QCM, which allows for the measurement of the deposition rate of not only neutrals, but also ions, so you can determine the deposition rate of different species. And other customizations which were included in these papers include custom temperature probes, different magnetron distances, in situ ellipsometry, and microwave plasma sources. So these are really nice papers because they leverage the modularity of the hex cell system to include a lot of different tools to come up with some really nice results. So the first paper we're going to look at was developing indium nitride films, and it was comparing deposition of these films via reactive high PIM sputtering and microwave assisted reactive high PIM sputtering. Indium nitride is a semiconductor material which is quite useful in optoelectronics applications. So we're going to look at the OES data first, and you can see here a couple of optical emission spectroscopy graphs taken from the paper, and these show the peaks of atomic indium, ionic indium, and also a variety of nitrogen species and ions. And this graph on the right-hand side shows the this is a kind of average of these OES graphs, and the bars which are of the most interest are these dashed bars here, and these show the ratio of ionic indium to, these show the ratio of atomic nitrogen to molecular nitrogen at different microwave plasmas, microwave powers. So why is this useful? Well, the OES data allows the researchers to see that the microwave sources facilitate the dissociation of molecular nitrogen into more reactive atomic nitrogen. So you can see that for the high microwave powers, this bar is much higher than on the zero power. And what this allowed the researchers to note was that the microwave powers really improved the stoichiometry of indium nitride in the final film. So the OES data just gives a lot more insight onto why that's happening. So the researchers could see that the microwave sources are really crucial in improving the stoichiometry of the final film. Another technique that was used is time of flight mass spectroscopy. So this allowed the measurement of the number and energies of argon, indium, and nitrogen ions in the substrate. And you can see a variety of graphs here. So the first thing that was measured is over a high PIMS pulse, the number of low energy to charge ratio ions were observed, as well as high energy to charge ratio ions. And during the high PIMS pulse, it was observed that these the number of all these ions peak. So in the time scale of the high PIMS pulse, around 50 microseconds. So this allowed the researchers to determine that the low and high E to Q ions were resulting from the high PIMS pulse. Whereas when they were looking at the mid E over Q ions, so you can see the same time scale here and then a much longer time scale here, these are present after the high PIMS pulse. So that allowed researchers to determine that they came from the background bulk microwave plasma. Another interesting bit of data that ties in with the OES data we saw before was that this top MS data allowed researchers to see that around the microwave high PIMS pulse, the ratio of atomic to molecular nitrogen ions, the ratio was around 40, whereas from the previous OES data, it was around 12. And this provided evidence that the microwave plasma facilitates nitrogen dissociation much more effectively than high PIMS. So this is just another example of plasma diagnostics really providing hard evidence for to prove or disprove a theory, which was that the microwave plasma might dissociate nitrogen molecules. Another thing that was used in this paper is a Langmuir probe. So these were placed at the substrate location. And you can see various bits of data that were found. So these graphs show at various microwave powers and nitrogen flows. They show the potential at the Langmuir probe, the average electron energy, and also the electron and ion densities. And a really interesting bit of data here is on this average electron energy graph. Figure B shows that when they put nitrogen into the chamber, the average electron energy actually decreased when there was microwave power. And this is because the electrons were imparting energy to nitrogen to cause it to dissociate. So this just adds another bit of evidence to the whole picture that the microwave sources are really making the nitrogen more reactive. And this is not something they would have been able to find out otherwise if they didn't have this Langmuir probe. Then another few graphs show the effect of the Hypens pulse. And you can see in this electron ion densities graph that the presence of ions and electrons at the substrate actually decreases during the Hypens pulse. And this is because they are drawn towards the negatively biased sputtering target away from the substrate. So it just gives you a very clear picture of what's happening inside your chamber, and it can really fill out the evidence that either proves or disproves your theory. So another paper that these researchers did was on aluminium scandium nitride films. And this is a piezoelectric thin film, which is useful for various sensors. And you can see an example of the setup of the chamber where they had two sputtering targets, one for scandium, one for aluminium. And they had these same microwave plasma sources, and then they injected nitrogen into the chamber. So one thing which is not a plasma diagnostic, but is quite a nice example of the Hexcel's modularity, is that they actually included in situ ellipsometry, and this confirmed the etching of native oxides on the blank silicon wafer prior to deposition, and this was using plasma cleaning. But on the topic of the plasma diagnostics, a modified QCM was used in this paper, and this determined the ratio of neutrals to ions and the deposition rate at the substrate. So the users measured the ionic flux density against nitrogen flow for two magnet strengths. So they have a weaker field here with this dashed line, and then a stronger field with the solid line. And this allowed the researchers to determine that the ionic flux was very high when they used the stronger magnet fields, the stronger magnetron magnets. And this informed the design of their experiments, because the high ionic flux was desired to maximize the dissociation of nitrogen to make it more active, and therefore make the best stoichiometry they could. So this is an example of the plasma diagnostic data influencing experiment design. And also TOF-MS was used again, and the data showed that ionic aluminium was present for quite a long time after the initial Hypens pulse, which you can see here in the gray. And this actually informed the choice of a substrate biasing pulse of around 300 microseconds. So again, another example of plasma diagnostics influencing experiment design. And the reason for this was because they wanted to accelerate those aluminium ions towards the substrate to maximize things like film density and hardness. And the final paper we're going to look at is not on nitride films, but they are on compound films. So in this example, 3 metal targets were sputtered. And this was done over a wafer which had a mask on it. And the idea behind this mask is that you can measure, during one deposition, you can measure multiple spots which have either silver-rich areas, zirconium-rich areas, or copper-rich areas. So you can come up with a lot of data just from one experiment. So sometimes this is called combinatorial libraries. And this paper was interested on the effect of pulse width on the ionized fraction of these metals. And this is an example of another customer which wanted to make very steep compositional gradients, and they made very steep magnetron angles and distances to achieve that. So in this context, OES wasn't quite as informative as in other papers because there was a very high density of emission lines. So it was important to have a variety of plasma diagnostic methods here. And in these images, we can see the HiPIM's current time curve and then some modified QCM data, which measures the ratio of ion to neutral in a variety of metals. So a really interesting point is that you can see with zirconium, for example, that the you actually have more ions to neutrals at lower pulse widths. And you can kind of build this into the HiPIM's current time curve and say, okay, well, maybe a larger pulse width, we're actually having some back attraction of those zirconium ions to the target. So that's why you're getting less measurement of ions at your substrate. So this is just another example that the plasma diagnostics really give you a lot of insight into what's going on inside your chamber. Whereas if you didn't have this, you'd kind of be going in blind and just randomly changing things with no real idea of what's happening inside the plasma. And the film properties were measured at different spots, and you can see that for different pulse widths, you got markedly different results over the same patch, and this was due to the different ionic species and also probably some kinetics that the ions are being accelerated for different time periods. But this just goes to show, you know, the massive differences that can happen in film properties due to small differences in your experiment. And without the plasma diagnostics, you really have no idea what's happening here. But with the plasma diagnostics, you can start to form quite a full picture. And moving on, we're just going to talk a little bit to finish off about the PVD chamber that was used in these papers and why it was quite crucial to the papers. So these papers used a Hexcel system, which can fit up to 6-inch substrates, but we have a variety of models of different sizes. And you can mix and match any of the different deposition sources we offer, so sputtering sources, evaporation sources, E-beam. And it's just designed to be like vacuum Lego. You can mix and match, upgrade, change things as you go along. But the really key factor in the choice of Hexcel for these experiments was the modularity of the Hexcel. So with conventional PVD systems, you often have a stainless steel chamber with welded ports or holes. And this is fine if you know exactly what you want from the beginning, because if you have a system for say 2 or 3 years and then you decide you want to change the position of a certain source, add a new source, or add a customized probe, it can obviously become very difficult because it's almost impossible to remove or add welds to an existing chamber. However, with the Hex, you have the unique characteristic that because all the panels are detachable, you can have the system for a period of time and then take off a blank panel and add on a new one, either with our customized source flange holes or any standard vacuum flange. And this facilitates the easy change of chamber geometry, so you can change substrate to target angle or distance, but it also allows the inclusion of customizations. So customizations which can be done in the Hexcel system. As we saw in the papers that we were discussing, you can include in situ ellipsometry or microwave plasma sources. And this was all done after the system was sold. So this was done with in-house machining labs, which really just shows how easy a task it is to change the system. And remember, these were used for confirming etching of native silicon oxide on the silicon wafer, or microwave plasma sources for enhancing the reactivity of nitrogen in the chamber for better stoichiometry. On top of that, you can also add custom panels with CF flanges for vacuum suitcase transfer or a cryo stage. You can add nanoparticle sources to the chamber or high power electron beams or ion guns for etching. And you can see here's just an example of a custom panel. So you can easily modify a panel. We can do that for you, or you can make it in your own lab. And of course, plasma diagnostics, temperature probes, and much more. So hopefully this part of the presentation gave you a basic good idea of why plasma diagnostics are useful in PVD, and a bit about why the researchers involved chose the Hexel to conduct their experiments. And I'll now pass over to Angus for Impedans part of the webinar, and he'll be explaining in quite a lot more detail about some of the physics of these plasma diagnostic tools. So thank you very much, and I will now pass over to Angus.
Thank you, Matthew. Just give me a second to get set up here, please. Tom, can you hear me and see my slides there, please?
Yes, you're all set up there, Angus.
Great, thanks very much. Okay, thanks for that, Matt. And thank you to the team at Korvus for inviting us along here today. It's great to be involved. As Tom said in the introduction, my name is Angus McCarter. I'm a sales manager at Impedans. And today we're going to talk about PVD and plasma diagnostics in the semiconductor industry. See if we can get this to move. There we go. So very brief outline. So just going to quickly talk about Impedans as a company. I understand we're gate crashing slightly.
I think you might be muted, Angus, if you want to just start again.
Hello, can you hear me? Hello? 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 Hello?
Yes, that's right. You're good there.
Oh, can you hear me now? Can you hear me, Tom?
Yes, that's good.
Perfect. Okay, so I'll just talk about Impedans in the company. Go right back to basics about what is a plasma. I imagine most of the audience here are familiar, but we just bring it back to basics, say what is a plasma, and then we'll talk about some of the plasma diagnostics that Matt mentioned in his section of the presentation. We'll focus on the Langmuir probes and the RFEAs, which are the ion energy and ion flux sensors. We'll then touch on some of the plasma diagnostic applications. There's a bit of overlap there with the ones that Matt showed us, and then we'll jump on to Q&A at the end. So very briefly, so we're an Irish company. We're based in Dublin. We're 20 years old this year. We were started by Professor Mike Hopkins back in 2004. We have about 40 odd employees, plus a global distribution network. Most of our staff are engineering background, so physics, plasma physics, electronics, software engineering, that kind of stuff. So we have a reasonably technical skill set in-house. Our core focus is to provide advanced plasma and RF diagnostics to plasma processing industry. So if you're using plasmas to do some kind of processing, we want to get involved. We hopefully have a diagnostic technique that would be of interest to you. Most of our customers are typically in the semiconductor industry, plasma processing, and university and research. So anybody doing sort of plasma processing research or development or production, they would be people who should hopefully be interested in our systems. Excuse me. So right back to basics. So what is a plasma? It's described as the fourth state of matter. If you consider the three standards, solid, liquid, and gas, if you start with a solid and you add energy or you heat it, it becomes a liquid. You add more energy or you heat it further, it becomes a gas. And then finally, you go into the next state, you add enough energy where you actually strip the electrons from the atom, so you ionize the gas. So a plasma is an ionized gas. It's a soup of electrons and ions. It's quasi-neutral, which means that there's typically equal numbers of ions and electrons. So locally within the plasma, there may be small electric fields because of distribution of charges, but in general, it's quasi-neutral. And it also exhibits some collective effects on the system. So why do we use the plasma? So in plasma processing, typically we have some fine features that we want to etch or deposit. We use the plasma because we can manipulate ions, which are basically the size of an atom, and we can manipulate those into giving us like an etching feature or a deposition feature. So we use the plasma to give us control over ions and electrons, to give us that very fine feature control. We also use it to activate certain types of chemistry, which can have which do processing on the surface. So typically we either etch, we deposit, or we modify the surface in some way. I understand this is fairly basic stuff, but we'll bring it right back to where we are. So the measurement challenges in the PVD process. So we've got the plasma itself, so that's what's actually doing the work. We want to understand the plasma, we want to characterize it, and we want to get as much information as we can about it. That gives us information about what's actually happening at the surface. It tells us, is our plasma drifting? Is it the same today as it was yesterday? And we also want to know, how is the plasma varying from the center to the edge? So you have uniformity process parameters that you want to look at, and also temporally as well. So if you're doing some high PIMS type applications where you're pulsing, you want to see, how does the plasma vary over the course of that pulse? Particles then from the plasma will deposit or will impact onto the surface of the substrate. So we want to know what's happening there. What's happening at the surface? What are the ion energies? How fast are those ions hitting the surface? What's the ion flux? How many of them are there? If we're doing some deposition, do we have ions? Do we have neutrals? What exactly is happening there? We want to get as much understanding as possible. And then finally, if where impedance are involved, is the power driving the process. You would, in many plasma processing systems, you would the energy you would use to create the plasma is an RF voltage or an RF electric field. That's a radio frequency field, and we have some diagnostics which can monitor that RF field and give you information about both the plasma and the process itself. So a little mantra or a little sort of slogan that we have in impedance is that without measurement of the process, you cannot control it. Okay. So let's delve in a little bit. This is a schematic of a typical plasma processing system. So let me just put my pointer on. There we go. So this is our plasma. Here's our substrate surface that we're processing. And this is typically under vacuum. So the boxes in red are where the impedance diagnostics would sit. So we've got our Langmuir probe, which Matt mentioned earlier on. Here on the surface, we have an RFEA. We have a couple of variants of that. So these measure ion energy and ion flux. And then here we have what we call our octave range, and there's a few different variants of that, but we've got a poly, a suite, a mono, an alpha, and a moduli. And they're the RF sensors. They either monitor the RF going directly into the plasma, or they monitor stray RF coming out through the window, for example. We can use these to infer information about the plasma itself. So this is what they actually look like, and I'll go into these in a little bit more detail in the later slides. So the standard plasma diagnostic is a Langmuir probe. We have a variant of that which is called the Plato, which I'll talk about in a few slides' time. The Plato is basically a Langmuir probe that you can use in insulating, or if you're depositing an insulating layer. The Langmuir probe doesn't work quite as well, and the Plato can overcome that. These are substrate level measurements. These are basically electronic wafers or electronic substrates. So these have sensors built into the wafer itself. So it replaces the substrate, and you can measure ion energy, ion flux, deposition rate, and things like that through this sensor. And then these are our RF sensors. So if you're using an RF-driven system, these would be of real interest to you because we can actually get information from the RF signature itself. You know, it's typically a sinusoidal RF wave, but the plasma is a nonlinear load, and that generates lots of harmonics in the carrier wave, and we can look at those harmonics and get information about both the plasma and the chamber system itself. So let's look at a Langmuir probe. So what is a Langmuir probe? So it's a measurement sensor. You basically insert it into the plasma, and then you can measure various characteristics. We'll talk about what exactly those are in a slide or two. It was invented by Erwin Langmuir, hence the name, back in the 1920s. So the technology is well understood and well maybe not so well understood, but it's certainly it's very well known. How it works is you just place it into the plasma, and the technique is you have if you're not familiar with how a Langmuir probe works, we have a conducting tip which is inside the plasma. We then bias that tip from a negative voltage to a positive voltage, and we sweep from negative to positive. When you're negative, you draw current in the form of positive ions. So unlike charge is attract. So if you're negative, you draw positive ions. As you sweep towards more positive, you draw negative electrons, and you draw a current at each point from the negative voltage to the positive voltage. And the shape of that, what we call the IV curve, or the current voltage curve, that's what allows us to get the information about the plasma itself. So let's look how we actually make it, or what it looks like. On the bottom right here, this is a picture of inside a plasma chamber. It's a capacitively coupled plasma. What that means is there's two parallel plates. So we have a powered electrode at the top here and a grounded electrode at the bottom. And then in the center, this is a shot of the Langmuir probe, and the purple haze is our plasma, probably an argon or nitrogen plasma, something like that. So this is our tip. And what we can actually measure, I think, like the plasma density, the electron temperature, floating potential, electron energy distribution function, and other parameters. And this is what the tip actually looks like. And we have this is what we call a single tip with a reference, and this is a double probe. And you would use different types of probe depending on the exact process involved. So again, we can use any type of plasma for capacitively coupled, inductively coupled, high PIMs, all this good stuff. So let's just push on here for a little bit here. So this is what we actually see. So as I described before, we have a conducting tip. We sweep from negative to positive voltage, and we draw current at each point along that, and then we use that shape to infer the information. So on this plot here, on the x-axis is the applied voltage on the tip. The text is a little bit small here, but you should be able to see this is the 0. Here we have negative voltage, and then as we sweep up to a positive voltage. And here is the current. This is the current drawn from the plasma. So the negative section, and this left-hand side, we'll go through the various points on this IV trace. On the negative side here, we're drawing ions. It's quite low compared to the electron side because ions are quite massive and they feel an electric field, but it takes them a while through inertia to get to the probe tip and be registered as a current. So you see a little bit of this little gap here is the ion current, and as you get down here, you get the ion saturation current. As you sweep up, you begin to get fewer and fewer ions reach the tip, and then eventually you get to the 0 point where there's no net current, so that's equal numbers of ions and electrons arriving at the tip. And that's our first data point. That's the floating potential. Then as you sweep up, you begin to draw electrons, and these electrons are basically the electrons you draw depend on the energies of the electrons themselves. And then you get here to this what we call the knee in the IV trace, this is the plasma potential, and then we carry on up to the electron saturation current. So this transition region is the interesting one. There's several, if not dozens, if not hundreds of PhD theses on this particular region, and this is the region where you need to apply the various analysis models to give you the information. And the characteristics that you get are like plasma potential, floating potential, electron temperature, electron current, electron density, ion current density, ion density, the Debye-Lang, ion saturation current, all that stuff. But what that does is that characterizes the plasma for you. If any of these drift from process to process, or from week to week, or from even within the process itself, or even across the plasma, you can use this information to help build a better process, build a better chamber, build whatever it is you're looking to do. And the benefit of our impedance system is this analysis. It's all built into the system itself. So you input some parameters like process pressure, gas, this kind of stuff, and then the plasma parameters are extracted relatively easily. So let me just push on here. So this is what you would see in an impedance system. So this is your vacuum chamber. You'll have some sort of a vacuum port here, and then this is the probe, which is a length of ceramic, and then there'll be typically a tungsten tip, or tungsten is quite temperature resistant. It works well with most process gases. If you're going to use oxygen or something like that, you would recommend maybe tantalum or something because tungsten reacts. But this is your Langmuir probe system. So the kind of things you can get like a time average or time result or time trend measurements. It operates in DC, microwave, or RF. So if in RF we put things like plasma filters in here, so we can basically block out the RF signal and just look at the plasma signal itself. Single and double probes, various lengths. We have linear drives, so we can actually scan during the process under vacuum. We can scan a probe tip across a plasma itself. and get the information on a, get spatial uniformity. We also have some rigid and flexible shafts as well. So this would typically be a rigid shaft if you have a nice line of sight. But if your chamber is slightly unusual or there's some furniture in the way, you don't have a convenient access port, we can have a flexible system which you can run a cable up to wherever it is that you want to run. And just some benefits here, it's all automated, it's off the shelf. It's kind of a rite of passage of a plasma PhD student to build their own Langmuir probe and do their own analysis, and it's a very useful exercise to do. But it takes a little bit of time. It's quite fiddly. You're never 100% sure if your system is built correctly, if your analysis is correct. Our off-the-shelf system has all the decades and decades of experience poured into it. So everything is, you can be confident that when you hit run, that the information you get is accurate and makes sense. What you can use it for is for automated reactor profiling. So that's just characterizing the system completely. And then finally, one is automatic tip cleaning. So you might get some deposition or some crud, for the want of a better word, on the tip. We've got a tip or a cleaning function where we basically draw a high current, and that heats up the tip and it burns off the deposition. Okay. So I'll just go back to this slide. So on the Langmuir probe, when you draw the current, when you sweep the voltage and you draw the current, it's a DC circuit, so it requires conductivity from the tip. If you're depositing a polymer or something like that, where you will eventually deposit onto the probe tip, and you build up an insulating layer, you won't be able to draw current anymore. We have another product in the bulk plasma measurement range called a Plato, and a Plato works in deposition plasmas where you're depositing an insulator. It looks and operates like a Langmuir probe in that you insert it into the plasma, but it's a different technique. We inject an RF carrier wave into the plasma, and then we analyze that signal to give you the information. So it's a nice little option if you want to use a Langmuir probe, but you're worried about depositing onto the probe tip itself. So let's look at some of the applications. So Matthew showed this application. This is from Bern University. So this would be using the impedance Langmuir probe. So this is the chamber setup. It's a high PIM system with a microwave booster for boosting the plasma density. And just very simply, we've got a Langmuir probe on a port here, and we put the port into the center of the plasma. So the reason we're doing this is we're using the time resolved mode. So it's a high PIM system, so there'll be a pulse. So on the x-axis here, we can see the time, we can see the increase of the pulse current, and then on the y-axis, we can see the voltage on the probe. But we can convert that then into the various plasma parameters. So I won't go into this in too much depth, but it's just to show you that you've got a time resolved option on the Langmuir probe. So here we have our plasma potential, our electron temperature, ion and electron density, and you can see how they vary over the course of the pulse. Again, I won't go into this in too much detail, but it's just to show you get this time resolved option on the Langmuir probe. So I'm going to move on now to our substrate level measurements. These are the RFEAs. We call these our Semion. It's the Semion range of sensors. So this is what they look like. It's an electronic wafer. This is a 300 millimeter option, and we've got these RFEA individual sensors. These dark gray regions are the individual sensors themselves. This sits on the pedestal, and then you run a cable out to a vacuum port, and then some electronics here and an electronics box, which just 19-inch rack power supply. And what you get is you get this contour map, which shows you the ion energy and ion flux, and it shows you that in real time. The software interpolates between the sensors themselves. So you build up this, the contour map, and you can see the energy and flux. And you see the image here. This is our test chamber in the lab in Dublin. And if you see through the window, you can actually see the Semion RFEA sitting on the pedestal. Okay. There's a few variants of this, which we'll talk about in a couple of slides' time. So we've got the main Semion, which is ion energy and ion flux. We have the PVC, which gives you time resolve. So if you're doing some sort of a pulsing or tailored waveform, or if you any kind of time varying aspect to the power generation, we have a PDC which can give you time resolve. So it gives you ion energy and ion flux and an ion energy distribution function, and it gives you time slices across that particular pulse. And then this is the quantum. The quantum is what Matthew is describing as the modified QCM. Our sort of brand name for that is the quantum. And that's a returning field energy analyzer. So it gives you ion energy and ion flux. But we've also built QCM, which is a quartz crystal microbalance, into it. So if you're not familiar, quartz crystal microbalance measures deposition. You have a quartz crystal which vibrates at a certain frequency. As you deposit material onto it, the frequency begins to drop, and you correlate the difference in frequency with the deposition rate. But if you just have a bare QCM or a QCM on its own, you will be measuring the deposition due to the neutral gas species and also the ion species which are depositing on the surface. With our quantum, we can repel the ions and see the deposition due to just the neutrals. So we get the ion neutral deposition ratio in the quantum, and I'll show you a little bit of that in a moment. So I think this was, Matthew showed a variation of this type of application. So this is a typical plasma system. We've got our substrate holder, and we've got a magnetron sputtering system. So what we're looking at here is the deposition at different driving frequencies. So we've got A, B, C, D here. So we're driving at 2 megahertz, 13.5, 6 megahertz, 27.12, and 60 megahertz. And this is a metrology, a SEM, where you can see what the material property is for each of these driving frequencies. But you might want a little bit more information about that. So what is the ion energy distribution function at these frequencies? So with our RFEA sensor, you can see here on the x-axis we have ion energy, and on the y-axis we get the ion energy distribution function. So we can see here the difference between the various frequencies. And you can see at 2 megahertz, you get this sort of very broad energy, but quite, it's probably a low flux. Whereas you've got in the 27.12 and 13.5, you have this quite defined peak. It's relatively narrow, so you have a little bit more control over the ion energy. So if you correlate this, let's say, for example, the 2 megahertz is your ideal, that's your ideal process, that's the ideal result. And then you monitor, you see, right, 2 megahertz, okay, well, that's the ion energy distribution function we want for 2 megahertz, or maybe 60 or whatever it happens to be. You can then maybe transfer that to a different chamber or a different system, or you can use that to maybe develop the process or optimize it. If you know exactly that, this particular peak gives you this particular result and you like that, then you can use that then to either develop it further or optimize it or transfer it from process to process. Or you run the process on a Tuesday and it's fine, and you run it on a Wednesday and it's rubbish, and you put your semi in and you take a result, you see, oh, hang on a second, the ion energy distribution has shifted, there's something wrong, there may be an air leak, or maybe your generator is malfunctioning or something like that. It just gives you a lot more information about your system. Now this is an application with the quantum. So just to go in a little bit of detail of the quantum system, fundamentally it's a retarding field energy analyzer. So we have a few grids here. These are our grid meshes within the button. So this is what our sensor looks like. We have ions which drop in through apertures here at the top, and then a cross section of this button is this section here. I probably don't have time to go into what each of these grids does, but the yellow grid is basically the energy discrimination. So you have ions which are dropping down into a collector. You discriminate you sweep the voltage here. And as you go into higher and higher voltages, only the more energetic ions can get through, and that gives you your ion energy distribution function. But we've also built a QCM into it, so quartz crystal microbalance. So if we turn all these grids off, all of the gas species, the neutral species, and the ions will hit the QCM, and we measure deposition due to everything. We then switch this on, and we repel the ions, so there's no ions, so only the neutral species can get through the grids. So we can see the ion to neutral deposition ratio. And there's Art et al. Have done some work. Erwin Kessel's group in TUE have done some work where we looked at the time on the x-axis and the QCM signal, and we can see the difference between deposition with and without ions. And that ion neutral deposition ratio is an interesting parameter to measure on your deposition system. So just a quick summary of what we do. It's very whistle-stop tour, quite high level. I just wanted to give you an introduction of what our systems do. So we looked at plasmas and materials processing. We delved into a little bit of Langmuir probes for in-situ plasma measurements, where we can measure plasma density, electron temperature, electron energy distribution function, floating and plasma potential, etc. Then there's the semi and RFEA for on-wafer measurements, with the ion flux at the wafer surface in real time. And then the quantum RFEA is ion and neutral deposition ratio. Really only scratch the surface, pun absolutely intended, of these diagnostic systems. I would encourage you to go to impedans.com, where on our resources section you can see a lot of application notes. We also have webinars where we really dive in, hour-long webinars where we dive into the nitty-gritty of Langmuir probe analysis or RFEA analysis or other applications. And I just wanted to give you a quick snapshot of where that is. Again, I just want to say thank you to the team at Korvus for inviting us along to this. I hope my connection held up so you could hear me. And I think now I will hand back to Tom and the team at Korvus, and we can probably take some questions.
Yes, thank you very much for that, Angus. Really great insight into Impedance's work, and thank you as well to Matt. That was a really in-depth look at some research papers that use Korvus products, and tied together with the impedance plasma. It really shows how both systems can be used in tandem to really push forward the research that's been done. So we do have a couple of questions that have been typed in, and if you have any other questions, feel free to add them in now. We'll try and get round to answering all of those. I'll start off with a question that is for Matt. So Matt, we have a question that says, as I understand it, impedance tools are normally connected via KF flanges, but your hex system uses unique rectangular flanges. Does it then need a special flange to connect an impedance onto a Korvus system?
Yes, it's a good question. So as Tom said, our flanges that we use for our sources are custom rectangular flanges. So the probes from Impedans, I believe, are on standard vacuum flanges, so KF or ISO or CF. So when we've done this before, we have made a panel with a standard KF port on it, such as a KF25, and then we've used a KF to CF adapter to then attach the probe onto it. But you could also make a panel with a CF flange directly on it and just attach the probe right on it, but it would have to be stainless steel in that situation. So there's lots of things we can do, and that's one of the main points of the hex system, is that you can very easily make new panels to accommodate any flange size you want to. So
thank you very much, Matt. And I have a question for Angus. Angus, what is the impact of having the probe closer to the magnetron or further from the substrate, and vice versa?
Yeah, so you can you can measure both. You can get quite close to the magnetron. It very much depends on where you want the information from. You can get pretty close to the magnetron itself. Typically, you want to make sure that you actually have a plasma there. If you get too close to a surface, either the magnetron or the substrate itself, you have what's called a plasma sheath, and that's a region which can be microns to centimeters in size. And the plasma sheath basically has no plasma. It's the edge of the plasma. There's always a gap between the edge of the plasma and the surface. So you just need to make sure, if you are measuring, that you actually have plasma in that region. And typically, if you can see it, you can measure. So if there's a gap at the target, or a gap at the substrate or something like that, you'll see a dark space. You're not going to get much information from there. It's just ions or electrons flying back and forth. But But once you're in the plasma, if you can see the plasma, you can take some measurements. But no, you can get as close as you want, just as long as there's actually a plasma to measure, if that makes sense.
Great, thank you very much. And we have another one here. What is the maximum power for the RF inline probe and RF spectrometer, and what are they rated for?
So we have a few different options. We have a few different form factors. The highest that we can go to is about 90 kilowatts. So we've some fairly beefy RF sensors that take up to 90 kilowatts. Yeah, and there's we can up to, I can't remember the exact, but it's well over 100 amps and kilovolt region in terms of current and voltage. Yeah, 90 kilowatt is a big one, but we can write down to kind of milliwatt and then all the way up to 90 kilowatts depending on what the exact application is. I hope that answers the question.
Great, and one for Matt here. Matt, are the 4-inch round magnetrons the maximum size that can be used in the Hexcel system?
So it's not the max size that can be used, it's the maximum size that we currently make here at Korvus. But in principle, you could put a 6-inch magnetron in the chamber with no problems. You're basically only limited by the chamber geometry at that point. And in that case, we would purchase a magnetron from a third party and then add it onto the chamber, like we do with a lot of different tools and deposition sources. So no, it's not the max size that can be fit in, but it's the max size that you can purchase from us as a full turnkey system.
Yep, thank you. And Angus, does Impedans have any experience with pulse laser deposition plasma? And would the Impedans products work in a chamber where the plasma is non-stationary?
Yes, we do have experience with pulsed laser deposition plasmas. Again, pulsed laser deposition plasmas tend to be a little bit more confined, so they're a little bit smaller than a plasma, a surface processing plasma. So again, you need to make sure that the probe tip is in the region where there is the plasma. If it's moving, that's maybe a little bit trickier. It depends on the details. If you have we've definitely done systems where you have a plasma region that's manipulated out through a magnetic field or electric field, and it's moving around a chamber. You might put the probe and have the plasma move through the probe, and then you have to synchronize it, so you're taking snapshots as it comes through. But yeah, pulse laser deposition plasma we can do. Again, there needs to be a plasma there. You need to be a little bit careful with the density of the plasma, but it can certainly be done. I don't. Well, we can. Whoever that is welcome to get in touch, and we can talk about the details.
Yep, and I've just got a last couple of questions. Another one for you, Angus. The impedance level, surface level sensors, do they have spatial resolution?
Yes, in that the substrate level sensors have several sensors built into them. So the spatial resolution is basically the distance between the sensors. So we have a 300 millimeter sensor that has 13 sensors on it. The spatial resolution is the distance between the sensors. It's of the order of tens of millimeters. So it's not like kind of millimeter resolution. If that answers the question, yeah, it's basically the positioning of the sensors. Now, if it's a particular application, it's not set in stone where those sensors are. We can move them for a particular application, but in general, they're maybe, I can't remember off the top of my head, but maybe tens of millimeters apart. So if you have a 300 millimeter diameter, you're getting one every 3 or 4 centimeters, something like that. Can't remember off the top of my head, but it's roughly that order.
Thank you very much. And the final question. Do you have any suggestions for a plasma diagnosis instrument that's suitable for microwave plasma CVD systems at around powers of 6 kilowatts?
For me, yeah, Langmuir probe will do it. We can use Langmuir probes in microwave plasmas. Again, just need to be careful of the plasma density. We can certainly do that. And similarly with the substrate level measurements, so ion energy and ion flux, If there's ions that are coming off the plasma, we can measure those at the surface. Certainly, that's the LIMR probe and RFEA. Our RF sensors obviously are not much good at microwave because it's the wrong frequency, but our LIMR probe and RFEA will measure. Yeah, no problem.
Fantastic. So thank you very much, Matt. Thank you very much, Angus, for that great presentation. Very informative from both of you guys. And thank you everybody for those great questions. Yeah, we if there's any more questions that anybody has, feel free to send an email over to Korvus Technology or directly to Impedans or any of the agents in your local territory, and we will get them answered. As I said at the start, there'll be a recording of the webinar that will be sent out to everybody who registered, and it will also be published on the Korvus website. And Angus, will it be published on the Impedans website too?
I believe so. I believe so, yes.
Great. Okay. Thank you very much, everybody.
Thank you.